I'm Juliana, a postdoc of the RL2 SP5 project related to the investigation of clogging issues on the emulsifier injection systems. More specifically, it is studied in the case of the peregrino basin, where Equinor manages the oil production. I initiated this presentation talking about the downhole chemical injection system, whose objective in the oil production is to deliver chemicals to the wellbore to guarantee a certain level of oil quality and by reducing the water cut and the viscosity of heavy crude oil. In this project, we focused on the injection of the emulsifier, non-ionic and the polymeric one, used to reduce the water cut in heavy crude oil at the peregrino basin. Thus, this system consists of a tank, one tank for the glycol. Here at the peregrino is used the butylglycol to flush the chemical injection line and to prevent hydrate formation, and the other tank that stores the polymeric emulsifier. Also, there is a pump and a control valve that regulates the chemical flow that is injected into the chemical injection line. There is an umbilical to the wellhead and a downhole injection valve that is particularly explored in this research, as these chemical injection valves has been suffered from clogging issues. Clogging means a block in the injection line which prevents the chemical injection, thus affecting the oil production. Clogging can damage the filtering system since precipitates can saturate the filter and cause blockage. It can also cause a blockage along the chemical injection line until the chemical injection valve and even cause its failure. The clogging issues can increase the production costs as regarding to the stoppages for maintenance of the equipment or to replace them, and this directly affects the oil quality of the oil that is produced in the well. According to the clogging observed in the chemical injection valves, some hypotheses can be raised about this problem. Maybe there is no chemical compatibility between the flushing fluid, the glycol or the butylglycol that is used in the peregrino basin as a flushing fluid and a hydrate inhibitor in this chemical injection line, and the emulsifier that is a polymeric surfactant, which is a block polymer with ethylene and propylene oxide groups diluted in ethanol. And even there is no chemical compatibility between these fluids and the clogging material. Also, changes in pressure and temperature along the chemical injection system might induce precipitation or even chemical gunking, in which the evaporation of fluids can form a viscous semi-solid material that can also absorb solids in its composition. The chemicals injected also might not be totally stable at the injection conditions and suffer from some aging effects of chemical degradation. As the last hypothesis, valve's mechanical failure can cause backflow of the chemical injection valve, and possibly there might be the clogging issue from this problem. From here, I will talk to you about the research carried out about SP5 project. We studied three chemical injection valves for this project that were used in the field and got clogged during the injection of the polymeric emulsifier. And we divided then all three chemical injection valves into 7 parts via teardown analysis to collect clogging material, to investigate if there were damaged parts in the valves or corrosion of the parts inside the chemical injection valves. And we noticed that the clogging material was mainly collected into the part 3 of the chemical injection valves. So here it's presented all the clogging materials collected in the 3 chemical injection valves, and here named as chemical injection valve A, B, and C samples, where the chemical injection valve B had 2 clogging materials at different points in the injection valve. Solubility tests showed the 2 chemical natures of the clogging materials, one inorganic and the other organic, with the sample from chemical injection valves A and C being soluble in water, and the samples from chemical injection valve B being soluble in toluene. These results are significant as they give us an idea of how the clogging material can be removed or cleaned from the chemical injection valves. Thus, the elementary analysis of the clogging materials also confirmed that there are 2 natures of the clogging materials via carbon, hydrogen, nitrogen, sulfur elemental analysis, where nitrogen and sulfur were not detected in the clogging samples. And we detected 2 nature of the clogging material samples, where the organic sample is rich in carbon, and the inorganic samples are not rich in carbon, which explains the solubility of the organic samples in toluene and the solubility of the inorganic samples in water. The micrographs obtained from scanning electron microscopy showed not a regular crystalline structure of the clogging materials from chemical injection valves A and C. Interestingly, the energy specific analysis revealed a great amount of sodium in the inorganic samples A and C. Investigating the inorganic nature of the clogging materials, it was found a significant amount of sodium as the cation present in their composition, detected via inductively coupled plasma analysis. Complementing this analysis, the anions that compose the clogging material were sulfite, and the phosphate, identified by ion chromatography, allowing us to conclude that the clogging material might have a composition of a mixture of sodium sulfate and sodium phosphate. FTIR analysis, or infrared spectroscopy analysis, demonstrated a similar infrared spectra for all the clogging material samples, A, B, and C, mainly presenting stretching from hydroxyl, methylene, methyl, and oxidized carbon groups, besides banding of methylene groups. These infrared absorption bands can be related to the components present in the chemical injection lines and present in the composition of the butylglycol, that is the glycol used to flush the line, and the components of the polymeric demulsifier, that is ethylene oxide, propylene oxide polyadduct containing as conservant diglycidyl ether, bisphenol A, and nonylphenol. And this could indicate to us that these components are adhered to the surface of the clogging material samples. Here is the spectroscopy investigation of the fluids collected inside the chemical injection valves A and B, whose infrared evaluation demonstrated an infrared pattern compatible with 2 butoxyethanol or butylglycol, indicated to us that the butylglycol is used to flush the chemical injection line and to prevent the hydrate formation at the emulsifier injection at the peregrine basin. Thus, it is also possible to conclude from this infrared spectrum that there is no significant absorption bands that might indicate chemical degradation of this butylglycol, indicating to us that this glycol is stable at the injection conditions. The compatibility tests between the fluids that might be present in chemical injection lines were conducted at three different temperatures. On close to the seabed temperature at 5 degrees Celsius. Other at 25 degrees Celsius, representing the approximately temperature where the chemicals are stored at the platform, and the last one at 80 degrees Celsius, representing the temperature almost at injection conditions. All the fluids were manually homogenized for 2 minutes and then visually monitored for 4 days at 24-hour intervals, considering a low flow rate of injection. From these tests, we can conclude that the butylglycol is not compatible with produced water, as they form separated phases, indicating that they are not totally chemically compatible. However, butylglycol and the emulsifier are homogeneous at all these conditions, indicating they are totally chemically compatible with just one phase along the period. This allows to conclude that the chemical compatibility hypothesis for clogging formation can be discarded, unless if there is backflow of produced water in the chemical injection valve. To investigate the stability of the chemicals at the closed injection conditions, maximum temperature and the pressure of injection with information informed by Equinor, the aging tests of the chemical fluids were conducted at 82 degrees Celsius and a pressure of 250 bar for 7 days, and a system consisting of a high-pressure pump and an oven to maintain the temperature of the sample along the analysis, and a sample vessel to storage the chemicals in during the experiment. This slide shows the emulsifier before and after the aging tests, here named as fresh emulsifier and aged emulsifier. There is not a significant alteration of its visual aspect, besides a light yellow coloration for the aged sample, with no detection of solid precipitates, proving that there is no alteration in the emulsifier properties and that it is stable for long periods at the injection conditions. Its rheological behavior maintains the same as a Newtonian fluid, and also its infrared spectrum not demonstrate chemical degradation after the aging conditions. However, when produced water enters in contact with the emulsifier, a brownish solid is formed at the aging conditions. Such a finding shows that if the brine enters in contact with the chemical injection fluids, that might be formed a brownish precipitate that could cause the blockage of the chemical injection valve's orifice, enabling us to elucidate if there is backflow in the valve. A brownish precipitate can cause the blockage of the valve, leading to a clogging issue. According to all the results presented, some conclusions might be highlighted. Butyl glycol and the polymeric demulsifier are totally chemically compatible. The clogging material has two natures, organic or inorganic, depending on the chemical injection valve source. Inorganic clogging can be removed from the chemical injection valves by cleaning with water, and the organic ones can be removed with toluene cleaning. Aged chemicals do not form solids, except if there is contact with the produced water. That is all for my presentation about SP5. I would like to thank you all for attending my presentation and the institutions presented here who collaborated with this work. Thank you again.